In the rest of chapter 3, we want to revisit an old friend, the exponential series that I've introduced in the section 2.5, I think, about power series. And I want to view this as a function and see that it has really some miraculous properties. We will introduce a lot of new functions and a lot of functions that you already know from high school probably, but now we see this formally defined and we see the kind of the exponential function is like an infinite source of beautiful mathematics, so to say. I've called it the section the exponential function, logarithms and powers. I first wanted to call it the exponential function and its friends, but it sounded too silly when written down on paper. So I decided for a more serious title. So we haven't talked about logarithms yet, and we haven't talked about powers with general exponents in the real or even complex numbers. We've only seen rational exponents so far, and this will change in this section, and for this we need some constructions involving logarithms actually. Okay, let me, just as a, maybe this section next should be more like a treat after the dry mathematics we've done. So now we see some new functions and to see some explicit proofs. I think it's also, everything is not too hard in these sessions, so I hope you will all be enjoying this. And by the way, preview in the next section, so 3.6, I will introduce trigonometric functions, so the sine and the cosine and so on that you probably remember from high school. Okay. Let me first repeat the exponential series, and so I've always called it the exponential series, and I've shown that it's a power series that converges everywhere, so I can consider this as a function defined on C, and when you consider this as a function, so like this really as a map from C to C, we call it the exponential function usually. It's the same as a series, so x from C to C, x of x, I hope you all recall, this is, don't need to define it, we've seen it, the series from 0 to infinity, x to the power of n divided by n factorial. This is the exponential function. Okay, we want to study this really as a function in this section. Okay, let me first summarize something or what we already know about these things, just the most important things. I will kind of, advise you to have the results from section 2.5 at hand, especially theorem 299, where I just collected some elementary properties of the exponential function. I will need some of them later, so it might not hurt to take a look every once in a while. Okay, what do we already know about this function? First of all, to stay in the context of this chapter, we've seen this is a power series which converges in all of C, and we've seen that the power series is continuous. So first of all, we know it's continuous, so this was corollary 43. X is continuous everywhere on C. Okay, and secondly, and that's probably the most important property that the exponential function has, we have seen in theorem 299 that the following holds: x of x plus y is x of x times x of y for all x, y, and c. And this theorem is so important that I draw a box around this, because this property is really crucial, because this tells you that the exponential function is doing magic. It converts addition into multiplication. So first of all, we add things and then get a result, the product of the two things. So it's really kind of the mediator between addition and multiplication, which are first of all completely independent. And this then shows you that the exponential function has a really crucial role in defining everything with powers and so on, where where we have these properties where we need to unite multiplication and addition. This is kind of the most important property. And since I like this so much, let me draw another box around this. Okay, so this is something that you need to imprint in your brain. And let me call this, need some space here. So theorem 229. Whenever I refer to this equation in this section, I will just refer to it by E. This is called the functional equation of the exponential function. But this is just the important equation that we need to know. So that's kind of the hero of the day here. Okay, so these two things we know, and so these are the two crucial properties, and just to save some notation, I want to just introduce the shorthand notation you probably all know, namely I just want to write e to the power of x instead of x of x, and this I will only use in this section if I have a real argument here. So this is not a contradiction to the notation with powers that we used to have, namely we have seen. So this is not contradiction, no contradiction to old notation, because we've seen that in fact, so E we defined as x of 1, if you recall. X of 1 was this number E, and we've really already shown in this theorem 229 that x of a rational number is always e to the power of the rational number. So this is where we really have exponents defined. So this is why this notation makes sense. So it's not a contradiction to what we did before. So this was by theorem 299 as well. So yeah, these two are the most important that we need for now. So continuity and this functional equation. Okay, first of all, I want to put this in contact with the previous section, namely in this section we will mostly study the exponential function with real arguments. So we will study this function e to the power of x, where x is an r. And we want to study this behavior and see how it, what it does. And first of all, we want to study some limits. Namely, we take some natural number or 0, then the following limits are indeed hold. The limit of x going to plus infinity of e to the power of x divided by x to the power of n, this is always plus infinity. And another limit, the limit of x going to minus infinity of x to the n times e to the power of x, this is 0. And this says that basically the exponential function has some very strong growth behavior. Namely, so just very generally, I will formulate this as a remark later on, but here we see that even if we divide out some power, powers are functions which go to infinity as x goes to plus infinity, so some really strong growing functions, but even if we divide out this power, this is still going to plus infinity. So this says that this really converges to plus infinity in a very fast way, namely it goes faster to plus infinity than every power. On the other hand, this limit has also an interesting interpretation, namely if we go to minus infinity, so this becomes then 0, but even if we multiply it with the power of the form x to the n, we know that if we have this power here, this by itself, if we just consider this on its own and that x go to minus infinity, depending on the of the index is, of the exponent is even or odd, this would either go to minus infinity or to plus infinity, but this will really explode. So even if we multiply this function here with something exploding, it still goes to 0, which means that kind of as x goes to minus infinity, e to the x is going to 0 very fast, so very strongly. So yeah, even we cannot even destroy the convergence by multiplying this with some power function. Okay, so this is kind of about the relation of e to the x to these powers, which is quite interesting. Okay, let us prove this. So for the first limit, this is actually easy to see, because for positive number of x, so of course negative numbers don't care if we assume this asymptotic behavior as we go to plus infinity. So if we have a positive number x, then we know that e to the x, this is strictly bigger than x to the n plus 1 divided by n plus 1 factorial. Because this is the exponential series, and this is one of the summands of the series. And if x is positive, all of the summands in this series are positive. So if we just pick out one of them and drop the rest, this will give something smaller. Makes sense. Okay, so we have this. Now, n was given, so if we just divide everything by x to the n, which is still a positive number, we get that e to the x is divided by x to the n, and if we divide this now, this is bigger than x to the n plus 1 factorial. And of course here we see this n plus 1 factorial, this is just some decoration, that's just some constant factor which is not relevant. If x goes to plus infinity, this here goes to plus infinity as well. So there we have the improper limit infinity. Since limit of x going to plus infinity x divided by n plus 1 factorial is plus infinity, so the improper limit here. Then you can use an argument which I technically haven't proven yet in the previous section, because now if you have some inequality here, if the lower of the two is going to infinity, is to plus infinity, then the bigger one has to go to plus infinity as well. That's about this kind of this, that wasn't part of the inequalities of functions I introduced, but this is what I will use here without proof. So since this holds, one derives that limit of x going to plus infinity, e to the x divided by x to the n is plus infinity as well. Okay, so this is for this simple limit. Okay, now for the limit of going to minus infinity. There we make a slight nice change, namely from the definition of limits of functions in plus or minus infinity. And this is something I haven't proven, but this is really easy to see. It easily follows that the limit for x going to minus infinity, and now x to the n, e to the x, this is the same as as the limit that we get when we let some other variable y go to plus infinity and replace x by minus y. That's the same thing. If we just take a look at the definition of these limits in plus or minus infinity, it just really changes sign and we get that this indeed coincides, and this is minus y to the n times e to the minus y. Okay, now we've seen about the exponential function, have seen in theorem 299 that, and this is something which is non-obvious here, that e to the minus y, that this is which would be the same as e y to the minus 1, and we've seen that this is the same, so as an inverse, so that this is 1 over e to the y. This was part of the theorem, that this really behaves how we expect powers to behave. So this means here we have minus y to the n, but since n is a fixed value, we can just take the minus 1 and put it in front. So here we get that the limit of x going to minus infinity, x to the n e to the power of x, is the same as minus 1 to the power of n of the limit of y going to plus infinity of y to the n divided by e to the y. Okay, now we've just shown that the reciprocal value of this, so the reciprocal function, this one here goes to plus infinity. And in the same way I had a theorem that, like for sequences, if a sequence diverges to infinity, the sequence of its reciprocals converges to 0. And this holds for functions as well, which I also haven't proven, I must admit. But this is 0 since since the limit e to the y divided by y to the n of y to plus infinity is plus infinity, since this implies the claim, so that this holds, in analogy with the corresponding theorem for sequences. So we could also use this doing sequences, so I will not really prove this at this point. So analogy with theorem 243. Okay, so we've seen that the exponential function has a quite distinctive growth behavior. And let me just say what this first limit means. I mean, I already verbally talked about this, so now let me just write this down. Loosely speaking, the first of these limits says that e to the x grows faster to plus infinity. So, of course, this is informally grows faster to plus infinity than every power than x to the n as x goes to plus infinity. So, tends to plus infinity, let me just write it like this. So, this is what this is not collision of notation. So, that this exponential function really grows very fast. This is what this said. Okay, so 2 more important properties of the exponential functions, namely those that we get if we restrict to real numbers. So first of all, here we could enter any complex number, but what if we only consider real numbers? First of all, x of a real number is always, as a result, a positive real number for all x in R. Then, So this means we get a function I will call x with index r. This is basically the restriction of x to r, but the only difference is that I go from r and this takes values in 0 to plus infinity, which is well defined by part A, which I still have to prove. So this function here, this is of course continuous. This is what we already know since this is a restriction of continuous function. Strictly monotonically increasing. Increasing and bijective. Okay, let me erase and I will prove these important properties. Sorry, haven't defined this function formally. So x r of x is of course just given by x of x. Right, so this is continuous. I'm sorry about messing up here the blackboard here. So this just means we restrict to these real values and consider this as a function with values in 0 to plus infinity. So this is why I use this new notation xr. Okay.